Hey, so today we're going to start talking about factoring polynomials. This is a new packet. So if you're not here, you can pick up a copy of the packet in the office, or I'll also upload this file so you can print it off, or you can just kind of handwrite some of the notes on here. So today we're going to go through page 1 of this packet, and tomorrow we'll cover pages 2 and 3. Today we're going to talk about factoring with the GCF, difference of squares, sum of cubes, and difference of cubes. So when we look at factoring, remember that's breaking apart our polynomial into smaller pieces. And there's several different aspects of factoring we have to consider depending on the type of polynomial we have. Do we have a binomial or a trinomial? And what is the degree, or what is our highest exponent? So first thing we're going to look at is GCF, which means greatest common factor. And when we talk about the GCF, it's whatever can go into all of the terms in your polynomial evenly. GCFs can have two parts to them. They can have a numeric part, so what can go into all the coefficients, and they can also have a variable part. So for the numbers on number 1, if you look at it, I started with 12a to the third plus 10a squared. 12 and 10 are both even, so I can divide out a 2, so I'm going to put a 2 in front. And then for the variables, as long as that letter is common to all the terms, you're going to pull out the smallest exponent. So I have a to the third and a squared, so I'm going to pull out an a squared. So I write my GCF first, which is 2a squared. And then to figure out what goes in parentheses, I divide my beginning polynomial by the GCF. So 12 divided by 2 is 6. A to the third divided by a squared is a. And then I take 10 divided by 2, which gives me the 5. A squared divided by a squared means I don't have a letter on that one. So my final answer is 2a squared plus 6a, or 2a squared, times 6a plus 5. Okay, so problem 2, same kind of thing. You're going to look for your GCF. So 14 and 7 can both be divided by 7, so that's the first part. Okay? They both have a letter M. And I'm going to go m squared because that's my smallest exponent. So my exponents are 8 and 2. I'm going to go with 2. And then for the n's, I have 5 and 2. They both have that letter, so we're going to do n squared. Okay? That's your GCF. That goes out front. And then you divide to figure out what goes in the parentheses. So 14 divided by 7 is 2. M to the 8th divided by m squared, so you're going to subtract the exponents to get m to the 6th. For the n's, you would do 5 minus 2, which is n to the 3rd. Okay, this sign is going to stay a minus because we didn't factor out a negative. 7 divided by 7 is 1. And then the letters are going to cancel out because m squared divided by m squared is just 1. N squared divided by n squared is just 1. So it would be 7m squared n squared, parentheses, 2m to the 6th, n to the 3rd, minus 1. And to check your work on that, you would distribute back. So if I multiply it back, I end up back where I started. And that's how you can tell if you've done it correctly. Okay. So GCF we practiced. It's just a little refresher of it. Now let's talk about difference of squares. So now we're going to get into what we call binomial factoring, which is when you have two terms and there are specific rules you can follow. The 3 rules we're going to talk about are difference of squares, sum of cubes, and difference of cubes. And we're going to start with difference of squares. This is one we've done before. But when we look at difference of squares, it's 2 perfect squares that are separated by a negative. When we talk about perfect squares numerically, it's like 1, 4, 9, 16, etc. Variable-wise, perfect squares are even exponents. So x to the 4th, x to the 6th, x to the 8th, x squared, or like c or whatever. Okay? One thing that's important, anytime you factor, and it doesn't matter what you factor, you got to factor your GCF out first if possible. So if you have a GCF, you've got to pull it out. Okay, so how do you split these up? If you have a difference of squared, an a squared minus a b squared, where a and b are just the square roots, you take the square root of each term. So for example, problem 1, 9x squared minus 49y squared. So the square root of 9 is 3, so you're going to write a 3 and a 3 in both parentheses. The square root of x squared is x, so that's an x and an x. So you've got 3x and 3x. For 49y squared, it would be 7y and 7y. So basically, you just take the square roots, and you're going to put it in two sets of parentheses, one with a minus and one with a plus. It does not matter the order you write them in. So if I had written 3x plus 7y, 3x minus 7y, those are the same thing. So as long as you have one with a plus and one with a minus, that's fine. Okay? So number 4, if you look at it, we have 72 and 2, and those are not perfect squares. So this one we have a little bit of work to do. So we have to factor out a GCF first. And our GCF in this case is 2. So we're going to factor out a 2, and you get 36c to the 4th minus 1. And then we're going to factor this, okay? So now we've got a perfect square separated by a minus. So 36c to the 4th, that would be 6c squared and 6c squared. Because 6 times 6 is 36. C squared times c squared is c to the 4th. I'm going to put 1 plus and 1 minus. And then for the 1, you're going to have plus 1 and minus 1. Or just 1 and 1. Okay. So there's your final answer on that. All right, now let's look at number 5. Number 5 also had a GCF, so I had to factor it out. And this time it was 7mn. So I got to factor out the number part and the letter part. And I ended up with 7mn times m to the 6 minus 4n squared. Then I look in the parentheses and I see that I have perfect squares separated by a minus, so I can factor again. Once you factor out the GCF, it's just going to stay there in front. And then you're going to split this part up. So m to the 6th would split into m to the 3rd and m to the 3rd. For exponents, when you take the square root, you divide them by 2. Now, that's not the same as it is for coefficients, but for exponents, you just split them into 2 equal parts. Okay? You got a minus and a plus, or a plus and a minus. And again, the order there does not matter as long as you have both of them. For the 4n squared, it would be 2n and 2n. So to check your work, you would just distribute this to come here and then multiply with the GCF. So you kind of want to work backwards when you check your work. Okay. Sometimes when you have higher order polynomials like 4th degree, 5th degree, whatever, you have to take an extra step. So number 6 is an example of that. Again, this time we don't have perfect squares to start with, but we do have a GCF. And our GCF is 10w. They both have the number 10, which means they can be divided by 10, and then they both have the letter w. So 10w to the 5th divided by 10w gives me w to the 4th. And then I have a minus, and 10w divided by 10w is 1. Okay? Now, if I look at my parentheses, I have 2 perfect squares separated by a minus. So I'm going to split it up. So I have 10w, and I have w squared plus 1, w squared minus 1. Okay? Now, this is where I said sometimes you have an extra step. So if I look at this problem, this second set of parentheses is still perfect square separated by a minus. Because w squared is a perfect square and 1 is a perfect square. So I've got to factor again. So I've got 10w, w squared plus 1. There is no factoring for perfect square separated by a positive. So that one's going to stay the same. And then this is going to split up into w plus 1, w minus 1. And that is your final answer. So that one breaks down into 4 pieces. And that's what factoring is all about. It's about breaking the problem down as much as you possibly can. So it is important to check your parentheses and make sure you factored them correctly. Okay, so that is difference of squares. Perfect squares separated by a minus. Now let's look at sum and difference of cubes. Okay? So perfect cubes are unique in that we have 2 different rules. We have a sum of perfect cubes, which is perfect cubes separated by positive. And then we have a difference of perfect cubes, which is perfect cubes separated by a negative. So we're going to talk about both of those rules. Now, perfect cubes would be numbers like 1, 8, 27, 64, 125, etc., where you have 3 things that can be multiplied together to get a number. So, for example, 2 to the 3rd. 2 times 2 times 2 is 8. Okay? 27 is a perfect cube because 3 times 3 times 3 is 27, and so on. When we go to factor these, we're going to be, instead of taking square roots like we did before, we're going to be taking cube roots. So what can we multiply by itself 3 times to get the number that we started with? Okay? Variable-wise, perfect cubes have exponents that are multiples of 3. It's like x to the 3rd, x to the 6th, x to the 9th, etc. So how do these break apart? There are 2 different rules, one for sum and one for difference. So for the sum of cubes, the rule is a to the 3rd plus b to the 3rd equals, and here's your factored form. The first parentheses gets a plus b, and then the second parentheses is a squared minus ab plus b squared. Okay, so here is how you break these apart. X to the 3rd plus 27, those are both perfect cubes. So the cube root of x to the 3rd would be x. In other words, you had to multiply x by itself 3 times to get x to the 3rd. For 27, that would become a 3, because 3 times 3 times 3 is 27. So you start off and you figure out what this first thing is. Then, to fill in the second parentheses, you take this first one and you square it. So x squared, it goes right here. This sign here is always a minus. You never change the signs in this formula. It's always plus, minus, plus. So the sign is a minus. A times b means you take these two and you multiply them together. So 3 and x. So it becomes minus 3x. Okay? And then for the last one, you take b squared. So 3 squared equals 9. So I wrote a 9 there. For the last one, since 3 squared, we can calculate it as 9. I don't write another squared up there. You would only do that if there was a variable involved. Okay, so let's look at number 8. M to the 3rd plus 216 n to the 3rd. Those are both perfect cubes, separated by positive. So, first thing I'm going to do is figure out what goes in the first parentheses. M to the 3rd, that means that's going to break into m. This is always a plus. 216 becomes 6, because 6 times 6 times 6 is 216. For n to the 3rd, it becomes just the letter n. All right, now I fill in the second parentheses. First one is m squared. Then I multiply the two things together, so it's 6mn, and that gets a minus because it's part of the rule. And then for the last one, I do 6n times 6n, so 6 times 6 is 36, and then n times n is n squared. So I have m plus 6n, and then parentheses m squared minus 6mn plus 36n squared. When you have two letters multiplied together, you always write them in alphabetical order. Okay, 9 and 10 are ones where we had a GCF. So you can see how I worked through 9. I factored out the 4, and then I broke it down from there. On number 10, we also have a GCF. So on 10, 24 and 375 can both be divided by 3. They also have letters in common. So c to the 4th, d, and c, d to the 4th. So they each have a letter c and a letter d. And I'm going with the first power because it's my smallest exponent. So 24 divided by 3 is 8. Then this becomes c to the 3rd. .375 divided by 3 is 125, and this gets a d to the 3rd. And the reason why this is c to the 3rd because I have 4 and I took off 1. This is d to the 3rd because I had 4 and I took off 1. Okay, so that's the first step, is factor out the GCF. Once you factor that GCF out, it's going to stay in the front. Then I'm going to take step 2. So 8 would become a 2 because that's the cube root of 8. C to the 3rd becomes a c. For 125, that would be 5. 5 times 5 times 5 is 125. D to the 3rd becomes a d. Okay? Then I'm going to use those pieces to build the second half. So now I take 2c and I square it. So 2c times 2c is 4c squared. The second sign on this is always a minus. Then you're going to multiply 2c times 5d and you get 10cd. 2 times 5 is 10, and then you just write the letters in alphabetical order. And then for the last one, you're going to multiply 5d times 5d. So 5 times 5 is 25. D times d is d squared. Okay, so that's sum of cubes. In sum of cubes, you never change the signs when you're using the rule. It's always the first parentheses gets a plus, and then the second it's a minus first and then a plus. Okay, last one is difference of cubes. It is very similar to sum of cubes. The only thing that changes is the signs. So in sum, you have a plus first and then a minus and then a plus. In a difference of cubes, it's minus plus plus, okay? So you will need to memorize those rules. You will need to write them down. You will need to memorize the sign pattern. Okay, again, you always factor out a GCF if possible, and the same rules apply as far as what's a perfect cube. So if you look at problem 1, it says x to the third minus 1. And so it becomes x minus 1 in the first set, parentheses x squared plus x plus 1. So x to the third becomes an x, 1 becomes a 1, and then an x squared. Multiply the two together, 1 times x is just x, and then 1 times 1 gives you a 1 at the back. All right, so let's look at number 12. That one's a little more interesting. Number 12 says 216k to the third minus 125. So we have perfect cubes. They're separated by a minus. So 216k to the third would become 6k. This 216 would be 6 times 6 times 6. 125 is going to become a 5. And since it's a difference of cubes, your first sign is a minus. All right. Then we take 6k and we square it. So 6k times 6k is 36k squared. This one's going to become a plus, and it doesn't matter what sign is here. This one's always a plus because of the sum and difference thing. Now we multiply 5 times 6k to get 30k. And then for the last one, you do 5 times 5, which is 25. And because I multiplied 5 times 5 and actually got a number, I don't need a squared on that because it's 25. If I put 25 squared, it'll become a much bigger number than I need. Okay. Number 13 is done for you. So 13, very similar. This time the variable's at the back. That doesn't really matter. The process is still the same. I did factor out a GCF of 4 first. Okay, now let's look at 14. So 14 also has a GCF, and our GCF here would be 2, because these are both even numbers, so I'm going to factor out a 2. So I've got 2 parentheses x to the third minus 27y to the third, so that's step 1. Now I have perfect cubes, so I'm going to factor again. X to the third, that would be just an x. This is a minus, so that's a minus. 27 would be 3, and then y to the third would become a y. So there's a and b, and then it's a squared, so it would be x squared. Then you put a plus, always a plus, and you multiply the two together, 3xy. And then for the last one, you're going to do 3y times 3y, which would be 9y squared. Okay? And remember, when you're doing sum and difference of cubes, your sign should always match the signs on the rule. So my rule said it would be, so this is minus, it would be minus plus plus, and I have minus plus plus. Okay, so for your assignment to go with this, I just want you to do skill number 1 on the Delta Math, which is factoring cubics, and there's only 5 problems to complete. So write down these examples, use this to help you complete your Delta Math, and do the 5 problems on sum and difference of cubes.